My name is Kevin Kocak, and I'm the founder CEO of Chemical Q Device. This is How to Succeed in PennyLane. It's a library for medical QML developers, quantum machine learning developers. And I wanted to start off, basically, there's a lot going on with quantum programming, and this in specific is a cross-platform Python library in specific for quantum machine learning. So other frameworks, they do other things. They might do more in different areas, but I would say PennyLane's a definite leader in this specific area. So when you try to wrap this, figure out what's important here, they use this term automatic differentiation for hybrid quantum classical workloads. Now, what this basically means is differentiable and trainable machine learning and artificial intelligence. So many of you may be familiar with deep learning, machine learning, where you're updating the weights and biases of that network. Well, in this case, you have another quantum algorithm that's also doing similar things, but it's primarily with the rotation of qubits. And the goal is to have these so that that they're syncing up correctly, that you're gaining from both the classical end of things and on the quantum end of things, either through a real quantum computer and or simulators. So I watched one of these videos this week from Xanadu, which has PennyLane. And they basically said for deep learning model ports it's coming over from classical. So you already have a model and you're porting it with trainable quantum algorithms. So a lot of times these will be like the rotational gates, RY, RZ. There's other parameterized gates and controlled RYs and so on and so forth. Now, the seminar is primarily going to focus on using PennyLane documentation. And in specific, their top 10 categories. After that, I'll go over 5 medical R&D applications utilizing PennyLane demos. Are there any questions at this point? Any questions or comments? Anything to clarify? And feel free, so at the end of each section, there'll be time for questions and comments as well. So this first part is quantum circuits. So quantum circuits is the crux of using, quantum in these hybrid models. So at the top, I put what you see a lot for QML.draw or QML.draw, and this is matplotlib, an image right there. And in specific, quantum circuits are represented as quantum node objects, and the quantum node declares the quantum circuit, and it ties the computation to the device. Now, the de facto is NumPy. Okay, so without having to change anything with interface, you're set with NumPy, and I know people that program, or at least one person that strictly codes in NumPy. Now, the benefit is basically this PyTorch, TensorFlow, JAX, these classical machine learning libraries, in hopes of also coupling this with updatable parameters with a quantum neural network, so you have artificial intelligence from both the classical end and the quantum end in the same notebook. So they use this term. So quantum circuit is constructed as a special Python function. Now, special Python function accepts classical inputs with operators or templates. So operators are gates and templates are collections of gates. The special Python function can contain for loops. This is in if statements, which is common in Python coding. And then also the special Python function returns a single or tuple of measurement values. It also is evaluated on a simulator or a QPU. Now, QPU is the abbreviation for quantum processing unit. You'll see these terms interchangeable with quantum hardware. The term device can mean either the simulator or the QPU. And the two biggest, basically the settings, for these, your quantum circuit are both the wires, which is a quantum subsystem, usually qubits. You can have qubits and qports, so on and so forth. And then shots. So shots, if you have a quantum device, and you can also do shots on a simulator, is the number of times the circuit is evaluated. Okay, so you could do shot bashing. So for instance, 1,015 shots, split it up. So 5 shots basically gets this performance, 10 shots this, and 1,000 shots. It's kind of like a convenience. And then QNode object equals QML.QNode. So this is what you see in a notebook. This is the special function plus the device. And then QNode may support multi-parameters based on operations for flexibility or performance boosts. Now, the QML decorator, you'll see a lot. They say actually to use this when you're using the @QML.code and then device, it converts the special Python function to a QNode circuit. So are there any questions regarding this? I know some of you might be coming from other, programming backgrounds or even quantum programming backgrounds, but it's basically, you have classical code, you're doing something quantum, and then you're returning it, just like it's a special Python function that did something quantum, and then now it's back to classical, like the binary you can do things with. Are there any questions or comments at this point? And then you could also post in the chat as well. So this section is gradients and training. So gradients and training is the crux of machine learning, artificial intelligence. If you're not calculating derivatives and this differentiability that PennyLane calls this, then you're not really updating parameters, loss function, and essentially an optimizer to change these parameters to help increase improvements every single time, every batch or epoch. So again, the NumPy, PyTorch, JAX, and TensorFlow is the key here. So automatic differentiation framework through the QNode decorator, which is this at QML.QNode. And you'll see here, so you don't have to specify the specifics. So if you're just doing things in NumPy, so you're not wanting to take advantage of a neural network from PyTorch or TensorFlow, NumPy equals default, so you don't need to do anything. And then if not, you do interface equals torch or interface equals TF for TensorFlow or JAX for JAX. And then this number 2 is really interesting, QNode conversions into other layers. And I've got a demo that you could use for medical data towards the end of this seminar. And it basically shows that you could do something with your classical notebook and then somewhat easily insert this layer that has quantum code in it as a QNN.Keras layers or a QNN.Torch layer without it sounding like having to reinvent the wheel with your notebook. So for those, this is kind of like that more advanced, say if you do dropout of layers, or if you're, just removing layers, if you've done that, this would make sense to you for this. And then also, so interface equals none. It is no automatic differentiation. There's no training. So there's no training, there's no machine learning, there's no AI. Now you do this for faster evaluation. So you're not updating parameters every single, so if you have 1,000 images and your batch size is 100, then you'd have to, so it's basically it's running that quantum circuit and updating parameters 10 times. And if that's a slow process, then that's a single epoch. And then if you have 100 epochs, you see what I mean? Like the time can really get to you if you understand what's going on in the background here. And then you'll see a lot of this, in some of the notebooks I run, you'll see that requires grad equals true, means that the machine learning is on. I think other purposes too, but I know it has to be on in order for the classical network to be trained at the same time as the quantum. So this is like that hybrid effect. And then not differentiable, set it to false. You also have GPU CUDA support. This is common in their notebooks too. Are there any questions at this point with gradient answer training or even the previous slide with quantum circuits? And you could also put it in the chat too. So I could read off the chat as well. And you'll see this. So NumPy quantum optimization, there's optimizers that already exist in Torch and TensorFlow, and I believe JAX too. And then there's also ones that have in mind that you're running quantum circuit like QNG optimizer, whereas an optimizer in NumPy for atom optimizer is more standard. Like that's from classical, without thought of running a quantum circuit. It doesn't mean that it won't work. It just means that the QNG optimizer is something with quantum in mind when they made it. And then also you have PyTorch optimizers. So torch.optim.atom, I believe, is running in one of my models. You have TensorFlows and JAX as well. Computing gradients. So I'll get into this a little bit, but you really have to understand this because there's differences between what you can do on quantum hardware and what you can do on a simulator. So when I say simulator, I mean quantum simulator that runs on a CPU or GPU and that takes the place of a quantum computer and can do some extra things that a quantum computer can't do at this point. So parameter shift, this differential method, it runs on both simulators and quantum computers. Now, simulators also have this adjoint method. So adjoint is propagation, which is deep learning, it's machine learning plus quantum reversibility. And this is thought to speed things up. I tried last night and it didn't work for my specific model, but it's one of these in theories. There's an advantage if you, I don't believe a probabilistic quantum computer can do adjoint. So say, for instance, the hardware plus simulators, they can all do parameter shift, finite difference, Hadamard. It's not the Hadamard gate, it's like Hadamard test. And if you're doing stochastic pulse gradients or pulse generator, that's like for pulse programming. So I saw a bunch of people come on. Are there any questions at this point? So you covered circuits. This is number 2. We're going up to 10. This is gradients and training. And then so number 3, and you could, feel free to, raise your hand at any point as well. Quantum operators refers to gates, noisy channels, state preparations, measurements for functions. So these above here, the Hadamard gates, this is a unitary gate on the left circuit there. These are sketches. These are not printouts. They have a certain effect you might like. So you see on the right, you have 2 Hadamards, 2 Z's, a control Z, and then 2 more Hadamards as well. And then, so also functions apply to operators extract matrix representations or transform operators. Another word you have to familiarize yourself with is transform. So with this being basically 10 slides, for the bulk of it, I didn't include all 12 of these operator to operator functions. You have operator to other functions. Some operator transforms can also act on multiple operators, matrix to operator functions. And then you'll see qubit operators. These are the ones most people are familiar with. So these are, non-parameterized or poly X, poly Y, poly Z. You have Hadamard gate. They're not trainable. Okay, so typically, when you see parameterized, it means that, if everything is set up correctly, that those parameters are optimized over the course of the run to improve the model performance. So non-parameterized gates, these should be, one's non, one's parameterized, is, the parameterized ones update over the course of the, the batches and the epochs and the final run. So you also have quantum chemistry gates specific for that. Gates constructed from a matrix, basis state, noisy channels. Now the CV gates are specific to PennyLane. So their hardware technology that they use is photonics. It's photonics based. So they've been in Nature for quantum advantage with a specific task using photonics. So it stands for continuous variables. So all these CV ones, I believe, are primarily for photonics applications. And Qtrits, which I've done in their demo before, and I can modify it to get a certain output of 0, 1s, and 2s. So it's not binary anymore, it's ternary. And so if Qtrit, different gates constructed from a matrix, Qtrit parameterize, Qtrit state preparation, which is in the beginning, which will take, like, say, if you're at the 0 ket state, then, it just changes the initial state. It's not something like rocket science. And then also if you're into pulse programming, which is for hardware pulse operator, and there's 2 of those as well. Any questions at this point? Questions or comments? And then, like I said, feel free to raise your hand if you have anything as well.
Hey, Kevin.
Yeah, go ahead.
You're number 3 on that slide. Previous slide.
Yeah, there we
go. Which is which?
Yeah, so I have to double check it. I'll have the deck up. So they're about the same. So some are parameterized, some are not. And then I'll have the link to the to PennyLane's, like, this is how you do everything too.
So one of those should be parameterized.
Yes. Yeah.
Okay. All right. Gotcha.
Any other questions? So on the actual PennyLane sites, this documentation, it lists all of the single gates, and it's just not something that I could do, in this concise PowerPoint format. So this kind of gets you that overview. Make sure catch the big points. When you go into circuits, you definitely have to know what a circuit is. You have to know what gates are, and then there's specifics to running on simulators, and then also with hardware too. So when you're talking about all this, you can't talk about, quantum circuits without measurements. Okay, so you can do things in quantum computing without measuring, but if you're talking about hybrid models, and especially machine learning and converting things back into binary, you're typically talking about measurement at the end. So if it's classical data, you embed, and then you have a variational circuit, and then you have these measurement gates as well here too. Now, in specific, the one that most people see is this QML.xval on poly Z. So this would be the first qubit. That's very common. And there's different ways. So you could use that method, expectation of an observable. Number 2 is its variance. Number 3, samples of a single measurement. Number 4, computational basis state probabilities. So there's 12 of these functions available, and all measurement functions support analytic differentiation with 3 exceptions. And this is specific typically for simulators with the analytic differentiation, a type of machine learning you could do on quantum simulators. And then they can also return combined measurements of multiple observables. And another term is commutable. So some of these are commutable. So say like a control NOT gate commutes, from the control to the target. Non-commutable would be more like Hadamard gate or a poly-X gate for those. List comprehensions, which is common from the classical world, and other common Python patterns are available as well. And then, you'll see a lot with, a lot of this comes down to what do you want the data to be after it goes through the quantum circuit? Like what form do you want it to be? So you'll see things like counts rather than samples. So it's basically, if you use counts, it's not as long of an array as if you use sample. You can also train QNodes on computational based probabilities using probs. Okay, so when I did all of this, you could also do mid-circuit measurements. So this is not specific to just, I thought it was just Quantinuum or IBM or whatever. You can do mid-circuit measurements in PennyLane. And this basically means moving one of these measures instead of at the end to the middle of the circuit to, typically if you do a wire cut or something at that point. Now, what's interesting about this is basically some of my demos had this, and I wasn't quite sure about it. So this number 7 is a Hadamard gate example on default.qubit simulator. So I can't include all of the text or in the code with it. But basically the crux of it is you could set the shots equal to 0. And I checked on, from a PennyLane researcher, and they said this is effectively infinite shots. If you think of it in the term that it gives the exact output as if a quantum computer would take infinite shots to do that. Now, so keep in mind, this is all in a default.qubit simulator, but it showed the result after 100,000 shots is still not close to 0. Okay, it's this 0.00056. And it's a simulator, so it's simulating stochastic random, basically you have a probabilistic quantum computer. So what this means is that the gentleman that responded to my questions said that, yes, it is preferred to have this infinite shots in some cases, right? So a real quantum computer, if you were to have real, machine learning, the whole thing, you would have to do 100,000 shots to get this result every time you did a batch. And then, like I said, if you have 10 batches per epoch, and then multiply that by number of epochs, that's a lot of epochs. And 100,000 shots takes a while, typically, for hardware to get to. So the other thing is this adjoint method for differentiation is right now only available on simulators. And so I don't think it's practical to do a real quantum computer, even if it didn't have noise today on some of these models. So, and again, the gentleman that Guillermo at Xanadu, who answered this question, said that it is specific to some applications you don't want exact expectations, but for the models that I've seen for them, I don't think you can use a quantum computer, like I said, even if it didn't have error and even if you had quantum speed up. So it's these types of things you don't quite pick up if you're reading a lot of, just full textbooks. And I mean, it may, but this one kind of surprised me because I wasn't aware of this, and I wasn't aware of the differentiation method as well. So I think when you're designing machine learning in QML, it has to be done in a certain way, keeping it in mind. If you're doing it on a quantum computer, what will the result be? How many shots will you have to take per epoch? And say, I really think it's going to be both of the technologies with quantum simulators and hardware in the long term, where say in this specific case, it's the quantum simulator, and then the quantum computer is doing something else where it's not having to do 100,000 shots for, more trivial applications to get the result down. So any questions or comments with this or previous slides? And then, so this is number 5. So templates are your friend, right? So I've used a fair number of templates on Qiskit, not as much as templates on PennyLane, but I've run more demos on PennyLane. And they can get you into trouble if there's too much entanglement, if it's too slow, these types of things, or if that's not what's contributing to your answer is more CNOT gates. But basically, it's a growing library of pre-coded templates, common variational circuit. So these are called ansatz. So ansatz is this term in literature that's used more so than templates. I think templates is like the consumer facing. It's a little bit easier to say or attractive than ansatz. But so it's to more easily build, evaluate, and train more complex models. You'll see it for embedding, layering templates, and you can get really creative. So this ties into like if you want a specific layer of your quantum layer in a torch, classical model. I think what it looks like is it's not this huge of a headache to take that torch or to take your quantum layer, say if it's ResNet 18, and now it's ResNet 17 plus a quantum one. So, it's basically it's a lot of fine tuning for QML or quantum machine learning at this point. State preparation, again, this is a simple thing in the beginning of a circuit, turning the 0 state into some other state. You also have quantum chemistry. Tensor networks is thought to be this a new thing, or it's not new, but more qubits, basic circuits with more qubits, and hence you can do more with the circuits with some restrictions. Swap network templates. You have a broadcasting function. They said beware. This could easily, chew up RAM and time. Parameter initializations with tensors. And also you could do custom templates. So that's another takeaway too, is that in most of these different topics is that you can do things that are custom. And I'll be getting to quantum data with basically loading, saving your own quantum data, those types of things too. Any questions? And again, feel free to put it in the chat. So if you've ever inherited a model or running a demo and you'd like to know what it looks like, this is kind of like, so if you want to use QML.draw, which is QML.draw, whatever your circuit name is, and these two are your parameters, this 1.22345, you could see in this specific model, it's text, but the parameters show up, but it's a little harder to read if you're not quite used to reading these. As far as like you see the Z measurement just way out there. But as far as I know, this is the default and you can see everything. Now, many of you might use matplotlib in your other notebooks, and this upper right-hand one does not show parameters. However, it's very attractive to look at, and it might be what you'd see more in a paper, right? So you have a quantum Fourier transform, icings, Toffoli, some swap gate, Rx, control RZ, and then measurement. So these two circuits are equivalent. And it's important to know how to use these. Sometimes it's not straightforward in order to know what you're doing, because a lot of times everything is text, or if you have for loops and it's not quite apparent what the actual circuit looks like, if that's really what you're trying to do. So I've spent a fair amount of time, with these two, especially the matplotlib, to try to figure out what was going on. But like I said, it's something worth the time to study how to draw a circuit. It sounds trivial, but if it gets more complex, it can be more complicated, especially with loops and these types of things. So basically allowing you to inspect, visualize, and analyze quantum circuits using transforms. Transforms is a huge word they use. New function accepts same arguments as QNode and returns desired outcome. And it starts getting into DAGs with these a dictionary of QNodes, properties, a matplotlib figure, or a DAG for connectivity. Now the specs function is cool. So if you ever use QML.about, which you'll see people using in the forums, which I recommend you to use, QML.about gives you your whole system to PennyLane researchers. And it tells them kind of like, your operating system, Python, all these types of things. Now, specs function tells you would put this in the cell of your quantum circuit, depth, number of gates, and number of gradient executions. So that's the last one sounds definitely like a time thing. So, you want fast circuits. Basically, somebody could look at it real quick and tell you how slow it is, or tell you how fast it is if it doesn't have much with it. So I went over this above, but I would really take a tutorial on just drawing circuits in PennyLane, because if you're doing demos and these types of things, a lot of times it's not the exact format from like the documentation that you would find. You can also take snapshots. So you can take snapshots in between wires. So you could put a snapshot, say, in between wires 0 and 1. And this is effectively, Qiskit and Composer has this where you can evaluate, at certain time points as the circuit runs. And here a circuit graph it's a class. It takes a list of gates or channels and Hermitian observables. And then here's this DAG as well. Commutation DAG. So a lot of these are getting into like, how are the individual gates interacting with each other? If you see like commutable commutation, that's typically what that means. Now, the last one with the parameterized quantum circuits and functions is you could get these outputs similar to these two drawings right here in a Fourier series of a low degree. And this is done through QML.Fourier module. Okay, so this is good to have under your tool belt, right? So even if you're not into this 100%, like if you're working in many areas in quantum machine learning, it's good to know that this exists, and then you can go research it if you need to go use it. Any questions at this point? And then, so this is number 7, so we're going up to 10. So this is compiling circuits. So compiling circuits is a huge thing. So for hardware, QPUs or real quantum computers, a properly compiled circuit can help minimize the effects of the noise associated with the computer, because you're basically running an optimized circuit and it's not being exposed to the hardware's noise as much. With simulator, it definitely saves on time and RAM. So if you're running on whatever CPU simulator, it's going to save CPU RAM. Then same thing with GPU RAM as well if it's a quantum simulator. And what's interesting about this is it says it transforms into one or more differing circuits. Now, the ones I put up top permute, and you'll see the differences between those two. It's basically moving the C0 gate in front or to the left on a time sequence in front of RZ. And then the two X's, they cancel each other. So it's a bit flip, so it cancels into 0, similar to an identity. Now, the last one, it's combining consecutive operators, meaning the parameters of the RZ are going 0.1 plus 0.2 goes to 0.3 in that one. Now, just-in-time compilation to me sounds like it's the next wave. All right. So a full classical quantum hybrid compilation into binary. So just in time. So instead of doing just quantum or classical, and I think it's used a lot in quantum chemistry with this program called Catalyst, is this sounds like it's the next thing, right? A lot of people research quantum machine learning in hopes of the quantum hardware to work and to get speed ups and bigger circuits, and other people more focus on the physics and you want to get better accuracy or a new utility with quantum simulators. So in both cases, I think that's desired. Like you always want an optimized circuit, whether it's a QPU or a simulator. Simplify function you could use as well, reduces depth, groups terms, resolves products, combines rotation gates as seen above. So all of these, so PennyLane is more a library, Qiskit is more a platform, and then the other ones. So Torch Quantum is probably more library, I think. TensorFlow Quantum more library. Google Circ might be more a platform. But in 3 or 4 of these that I've seen, you'll see there's a lot of work done between, if I want to design a circuit, that might not be the best way that the computer can run it. So that's what compiling does, is it basically turns it into machine code, or you're trying to get to that point where it's just running more efficiently on the actual machines. And then you have compilation transforms and circuit cutting. So circuit cutting is, you could get very creative with circuit cutting. So they say of a circuit with n wires by a set of circuit with less than n wires. So this means that, say, if you have 0, 1, 2, and 3 as far as qubits, then you can have 0, 1 in one circuit, and then 2 and 3. And basically you can activate that with wire cut. So I've come across this a little bit, but you really have to know what you're doing. It's like, it takes practice. I don't know if they have just a wire cut one. And then at the end of all this that just took place, PennyLane, just like Quantinium or Qiskit or the other ones, automatically combines results of the fragment executions to recover the expected output or expectation values, meaning that after you did compiling, it's still the same answer. It's just running better on the quantum computer or the simulator. And then you can use cut circuit. I think this is Monte Carlo chain as well. And then here's another commuting. So mutually commuting poly words can be measured simultaneously on a quantum computer. And then you can also use this split non-commuting. Are there any questions regarding this, regarding compilation? So a lot of times you hear the term transpile. One is, basically high to low level. I think transpile is high to high level as far as programming languages. Okay, and then number 8 is quantum chemistry it's an emerging field because the data is essentially quantum. So there's a lot of experiments that have been done. We know about specific atoms and molecules and charts of data and all this stuff. So I think that's the main thing, is you're not typically starting off with classical data. The requirements can go high, right? So I haven't seen too much more than like, hydrogen molecule or, too much more than that. Basic linear molecules but like, I think water is a little bit harder because it's bent. So basically it's dealing with molecular dipole moments, spins, and particle number observables, net charges, spin multiplicity, atomic basis functions in the active space. So the interesting part is that it says you can import from an external file with this. So figure all these, this library and other platforms, the whole goal is to remain that everybody's, the industry is moving forward. And say, for instance, like Qiskit has opened up for Torch connector. I don't know about TensorFlow or JAX at this point, but they're not like the same company. It's to keep the users, coming from all these different classical platforms. And so they have different casts. So the quantum computer prepares the trial wave function of a molecule and measures the expectation value, meaning like the answer, but the classical optimizer is used to find its ground state. And you'll see a lot of this, like the quantum and classical, like just-in-time compilation, like I talked before. And then this one is, there's, it's the Hartree-Fock that does both classical and quantum. So you have all of these tools to work with, integrals and matrices, Hartree-Fock, with external packages, molecular class and bases. Are there any questions regarding this, quantum chemistry? And then this is what really interests me. Okay, so medical image analysis is what I've done a lot with, and I've used some of their models and demos and all this kind of stuff, but it uses classical data. Now, what they say here is you could use the data sub package, it's lowercase data, to download, create, store, and manipulate quantum data sets and access data of a desired type, load interactive, these types of things. And as it makes sense, you don't have to do the whole thing. So you can do multiple parameter values and, get snapshots on these types of things. So I haven't had a time to see if it's just quantum chemistry, because a lot of this is related to that. It's number 9 compared to number 8, but it's a very interesting thing because there's other quantum data sets. There's MNISC with a Q at the end. There's Q data set. So these are basically, it's running a data set as a quantum circuit, and you're skipping the embedding layer. So there was a question, well, can't you just turn classical data into a quantum algorithm before you even run the circuit? And these types of things, these questions and these kind of, good ideas will continue to evolve. Are there any questions regarding quantum data? And then this last one with QNode Returns is basically, when they update their software, the previous versions had, previous to 0.30, is this NumPy, NEP34, and constrained NumPy compatibility. So anyways, before 0.3.0, you'd have these, you may encounter this where you experience breaking changes or issues when upgrading to the new PennyLane version. Now, there's updates all the time in quantum software. So Qiskit all the time. I wish I knew the schedule, because sometimes some people can't get on, or it's just the hardware's not working or something like that. Now, they all do it, right? Because it's not cemented yet. Like, the field is still evolving, and, it's important to make things right. And, for users to stay on the balls of their feet a little bit, having to upgrade to a new system, because, it's not like it's not like classical programming where things are pretty, cemented. Now, a lot of people may ask, well, how do I get involved? And I would say definitely be active on the contribute to the Xanadu discussion forum. This is, Xanadu owns PennyLane, but it'll say Xanadu at the top. And a lot of times you can ask questions, this is encouraged, but hopefully you get to a certain level where you can start helping other people. And it doesn't have to be because you're this awesome programmer. It could be that you're resourceful because you know where the documentation is, because some people don't read it, and you can point them to a link, these types of things. But I think it's a mix, right? If you're working on notebooks, you're going to have questions. And at that same time, there are newer people. And I would say this forum compared to Qiskit is a little bit more straightforward, because it's just typically quantum machine learning and their demos. Qiskit, there's many, many things. But I would say in QML, the bulk of the papers that I read, they're typically PennyLane. They might do a comparison between the two platforms. But for quantum machine learning, this is the thing that PennyLane focuses on. So also, they have over 140 demos, and they're all free. You just download the notebook. It's .ipymbs, or you could do Python scripts. And there's also, I think, another 30 or so user demos, and those are in specific are typically more complex. They're in papers, but they're using PennyLane code. Now, what I see in the future is basically more deep learning with quantum compatibility. And this is by watching, YouTube videos, and, they'll go on and say, this is our strategy, is take an existing, deep learning model and just, port it with quantum. And then the JIT, just-in-time compilation, seems like something that makes sense. So it's compiling at the same time, with quantum and classical. And then hardware, it'll take on additional compatibility and capabilities. The question is just how much. Because in some things, yes, like if you get over 30 qubits, you're typically faster on a quantum computer, and you can run, bigger quantum circuits, but then you have noise. And then likewise, quantum simulators, no noise whatsoever. You have more differentiation methods, and then, some analytical techniques that you don't have to do shots, like you just get the answer right away. So, okay, so everybody coming from medical, you should check these out. Now, I wouldn't say I've run these first two a lot, especially the first one. I've done like, many classes and images and all these like, time cost efficiency studies with the specific one. And I could change out the ResNet 18 for 50, up, bigger circuit, get better accuracy at the cost of time, these types of things. But this one, it starts with the binary classification, ants and bees. You just, upload your own binary classification with medical images. Lots of people have used this, and it tends to work well. The author, Andrea Mari, he also created the second one too, and it's more for like standard data sets, like Keras.datasets, and you can do FMNIS or CIFAR, those types of things. But you could also likely port it over to something like a medical or MNIS, these types of things. And then number C, or letter C, equivariant graph embedding. If you have data in the form of graphs, this is one to check out. It's actually not that long. So this C, so it's that, that's the reference there, is the L1. Tensor network quantum circuits. So this is basically more qubits with medical data. And I did check out this one. I was able to create the MPS circuit, the tensor network, which is kind of like the matrix product state, which is kind of a standard, but had issues running it in a different model. In fact, the first model, the A. And the last one is the one I'm excited about because it sounds like it's a lot less of a fuss to create a whole new model. And this sounds like it's more like you're, doing quantum code in a certain way. And then now you have this additional or replacement quantum layer, so instead of like, an 18 or 50 layer ResNet, now one of the layers is a quantum layer. So these are the references here. Are there any questions regarding that as far as running, specific running, demos? There's like over 140 of them. Which demos to run if you have those type of questions. And anybody in the chat, like, have you started with PennyLane? And if so, kind of where have you gone to? And then have you seen any cool papers that use PennyLane as well? So we have a number of new people here. So is it Samuel? So Rufino or Dino? Go ahead. Do you have any questions? And then if not, we have some returning people. So Ron or Edwin?
I've only run a couple of programs on PennyLane as part of a summer school, and they were more related to very simple hybrid QML models, and they didn't actually even state the goal of the model. It was just more of how you write the circuit to pass the parameters back and forth between the parameterized quantum circuit and the classical stuff.
Yeah.
But it's very it seems like it would be very powerful. So
Yeah, I mean, like I said, the quantum transfer learning demo, I think has all of the working pieces in it, and you can upgrade the ResNet. It's pretty simple, just changing elements. But I would recommend that to anybody, as far as like a full thing. Like if you're getting past that stage of just like, smaller, parts of the circuit, now it's something bigger. You will learn in different ways. I've learned a lot from researching this. I read it 3 times. And I learned a lot from running demos, right? Because I could just see in the code and I could just search on the internet, what does this mean? And a lot of times it's classical, and that's just how it is. But the more recent ones they have coming out, I mean, they had a pulse that was very interesting that I ran. So this is for hardware. They had the just-in-time compilation. I thought that was really cool too. But yeah, it's going to remain focused towards quantum machine learning. I don't think it's going to, move too far from that. Any other questions? Do you have anything? So it was interesting. I joined this, I think it was a Bay Area discussion, physics with friends this week. And there's a gentleman that does everything in NumPy. So it's like the whole circuits. And he's like, I don't even think Qiskit could do this. And that was the first time I heard that, because when I think of Qiskit, I think very, technical or like, fundamental. So yeah, I mean, there's a bunch of programming techniques out there, but it depends on what your focus is. So if you want to change the physics of your quantum simulator and run, Qiskit dynamics and these types of things. But I think, to me, because quantum machine learning is the #1 application in quantum computing, that it makes sense to really study, this is definitely one of the leading, if not the leader in QML for code.
Yeah, I would say that if you're just starting, it's okay to look at the toy problems, even though they're not gonna be good for anything. It gets you the basic components lined up. If you jump into one of the projects where they're loading a ResNet as a layer, the thing gets big and unwieldy pretty quickly. But it's just the important understanding of how your quantum circuit becomes a piece of your ML model, and the mechanism you use for like you were saying before, Kevin, you're actually training the parameters on that quantum circuit. So in that case, you're doing your back propagation, your cost functions, and then one of those layers has to come back and adjust the parameters for your quantum layer, and then the quantum layer uh, just becomes another layer of your ML stack. And again, the I think it's okay to start with toy problems that have no real purpose, but just demonstrate how the code goes together in very small chunks. So you get a really good foundation, and then you can go on to the bigger pieces.
Yeah, I mean, as far as like what's in between, because I watch a lot of the YouTube videos, because there's certain things I don't pick up, just running demos and reading documentation, because they'll say like, okay, it was actually harder for them for the quantum transfer learning model to do the deep learning end than it was the quantum part. And that's what they said is like, that's their approach, because, that makes sense. I don't think quantum algorithms and designing new quantum algorithms is going to be the struggle. I think it's more of the meshing between training and QML. The classical neural network, the quantum neural network, have things line up and not overfit. So there's overfitting, in some of these if you do things too well. So, and that's apparent in classical too. I put in the chat, so there's some demos there. And I think the hardest thing for some people, I mean, I go to San Diego Python, Boston Python, and all these, AI groups, is just pushing play, So if you find a demo you like, you just download the model or the notebook and then run it in a Colab. You have to do pip install of PennyLane. But other than that, it should run. Most of them that I do, they tend to just run, make sure to install PennyLane. And unless there's an issue with a local IDE that, you can run it in Colab, it's like a fresh start. So, but yeah, you go back and forth, right? Like you have to find out what to do. And if it's due, then you run a bunch. And then I got in this habit of running overnight, for something that was just getting a little bit better accuracy, but I didn't figure this out till afterwards, right? Because the quantum circuits are slow and, sometimes like 7 to 10 times slower, but trying to get that performance boost and accuracy over like the competitor classical model. Anybody else? Edwin or Marson? I'd be interested to hear what people want the most out of quantum. I think for me, I have settled on QML, quantum machine learning, and that's the primary focus. So for those that missed a little bit earlier, this is talking about training parameters and automatic differentiation, and it trying to get that right with classical to get AI from quantum and AI from classical at that same time. So I think that's definitely within the reach of a big research paper coming out. I don't see why not, like understanding the physics better and how your data sets process. Go ahead, Edwin.
Hello. Yeah, I think it's really interesting your your presentation and getting to see all these resources that are on PennyLane. Yeah, but I still haven't ran like a quantum machine learning model. It's still an interest. But I was wondering maybe whether most of the papers on archive have the code, whether
Do
it's
they have code?
accessible. Yeah, yeah.
I wouldn't say so
For the
as a
model.
standard. There are some. So Maria Schuld at Xanadu, she has linked code like her GitHub to the archive. I've seen that. Now, I say for instance for quantum transfer learning, if you search for that on GitHub, people have used that with text, images. They've taken it far. I've taken it pretty far. I haven't had issues with training on the quantum side. But as far as like proof of concept with many classes and, doing cost, time and efficiency studies, these types of things. But I think you'd be surprised that QTL model is one of the more developed ones because it's so, I even got a transformer to work just with minor, well, I can't say minor, with some errors, so transformer is kind of like an upgrade from a CNN in some regards. But yeah, if you do quantum transfer learning, it's likely going to be that model from Andrea Marie. And I'd asked him a question. He said, "Oh yeah, you'll figure it out." And I figured out the understanding of it, and then the next step is actually to take it further.
Okay. Interesting. Okay. I'll check that out.
Yeah, and keep in the back of your mind how efficient some of these are. And say for instance, data re-uploading, you can use like 1 or 2 qubits, or I've seen it with a qtrit or above, and it's classification like QTL, but it's a lot. It's say for instance, you're not going to use nearly as much RAM or use as much time in that specific model, in theory. So I asked, Xanadu, I was like, "Are you guys working on this?" And they said, "When I figure it out, I can post my model up on the community." But to me that makes sense, right? Like do 10 class classification on a single wire, and when you add more wires and more CNOT gates and entanglement, you tend to get exponential run times and exponential RAM, right? So you don't want those two. Go ahead, Ron.
Okay. Thank you.
Yeah, just to follow up for Edwin, like I said, I ran a couple of tutorials on PennyLane, and I had access to a free tier account. I'm sure I still have the account. I don't know how long the free tier might have lasted. It was connected to a summer school. But if you can go over there and find, set up an account so that you can log in and and find out whether they have a free tier, it's going to be limited. You're going to be limited to a certain number of everything, qubits, whatever, RAM. But again, it's just that first step of find the toy problems that are small and easy to look at when you go to draw the circuit and stuff like that, and start there. And if you can do it for free, you can spend all the time you want on it at that tiny level, and then decide whether it's something. Because eventually, if you start doing big things on PennyLane, you have to subscribe or get a subscription, and pay them money for access to the hardware.
Okay.
Yeah.
Interesting.
I
I'll
mean,
try that.
you should get at least 8 gigs. That might be in North America, but I haven't had much issues with RAM with Qiskit. But just keep in mind, so if if you have a big data set, big quantum circuit, so Guillermo from Xanadu kind of, responded to one of my questions, and he said, if it's, especially the bigger circuits, if they're, you have to keep in mind entangling gates, number of qubits, especially. There's a paper, I think I shared it before. It's it's challenges and opportunities in machine learning. And then they had a follow-up to it. It's the trainability one. I don't know if you guys saw that one, but those two papers I would definitely read, because they say for barren plateaus, which is gradients like landscapes and, loss functions, optimizers, these types of things, is, C0 gates, global measurement, like measurement on every single qubit, and the, number of qubits. These tend to create barren plateaus, so your loss landscape is not as favorable. So I would definitely check those two out. Actually, I've been meaning to share this. It's actually, he used to work at Los Alamos National Laboratory, and his name's Patrick Coles. He works now at Normal Computing, and let's see. I've got it's from a Q hack. So apparently there's been 3 Q hacks. These are all PennyLanes, by the way. Q hacks are developer conferences that Xanadu or PennyLane runs, I think, in the summers. And this one kind of stuck out. So I'll share this one. Yeah, I can share all 3, looks like. So I put those in the chat. So it's a combination of things. And, you have to be aware of, say, for instance, there's differential programming for machine learning that only simulators can do, that's technically better than hardware at this point. And, shots issues, if you run X, million shots per batch and, epoch, and it just, that's not going to work. So you would have to use a quantum computer in those cases where it's not so time consuming. And we're not even talking about noise, and there's quantum noise there too. So
yeah, Kevin, I think you mentioned in your presentation and your slides that PennyLane likes to use Python decorators. So I would encourage people to make sure what those are, and maybe not worry so much about how to build them, but know how to use them and exactly what they do. The short, simple explanation is they jostle all kinds of stuff behind the scenes and put a wrapper around a function or an object, and it's a very powerful tool. But every time I have to go build one, I have to go reread the specs on it, because it's probably the most complicated thing in Python land.
yeah.
I've also noticed that some other frameworks were also used, and it might be PennyLane, use some more advanced features of Python, like operator overloading and certain other metacoding techniques, like object factories, method factories, that sort of thing. So make sure you have a good idea. Again, you don't have to worry so much about how you build them, but just understand, what a object factory is, or a method factory.
Yeah, I appreciate that. I mean, when I read documentation, it seems like, there are multiple formats. Say, for instance, I don't know if it's specifically for decorators, but when you're building circuits, and especially for Q nodes, for instance, like, you don't need a Q node unless you start interacting with other, classical, neural networks, classical code. So yeah, you have to go to QNode. Then they say to recommend the QNode decorator as the next step. But they say it's easy to use.
Yeah, and the beauty of the QNode decorator is that you can just write your quantum function, and it doesn't have to have any knowledge about where it's going to be used. And when, again, a decorator, the simple explanation is it puts a wrapper around it. So if you build a quantum circuit, I believe it has to be a quantum circuit, and then you decorate it as a Q node, then that just automatically sucks it into the PennyLane system and takes care of all the details of mapping arguments and parameters back and forth between your code and whatever you're running it on, whether it be a simulator or actual hardware. But the beauty of it is here's a word that I don't want people to get confused. Decorators are design patterns, and they're designed to eliminate entanglement, not the quantum kind, but the programming kind of entanglement. And what that means is the code that you write doesn't have to know anything about how to get run. Decorating it with a QNode takes care of that just by wrapping it up, shuffling all kinds of stuff behind the scenes for you, and it just magically happens. So it's cool.
Yeah, that's interesting. And you're saying so it's the same exact thing for PennyLane QNodes and QNode Decorate. It's like it's a Python thing more than like a PennyLane.
Well, when you put it in the code, it's an @ QNode. So that, and you have to put that right in front of your object or your circuit or whatever it is that you're decorating. And then what it does is it puts a wrapper around, let's say it's a circuit, it puts a wrapper around the circuit, and it's all of a sudden that circuit just becomes eligible to run in the PennyLane environment. And you did nothing but decorate it.
Yeah.
You didn't have to map anything. It's all handled for you.
Yeah.
It's a very powerful. I really like it when I see some of these frameworks use the more powerful features of Python, because if you sit down with me in a few beers, you'll know that I don't like Python that much, but it does have some extremely powerful features, and those are some of them. And I use Python because I don't have a choice. Everywhere in science, pretty much everywhere in quantum land, it's all Python. Yeah, there are frameworks in other languages, but the bulk and the majority of it is Python. So get good at Python.
Yeah. Now, I mentioned a little bit earlier, there was somebody out there that does everything in NumPy, and that person might be in our chat right now. So, Paul or anybody else, if you want to talk about that. But, we were talking about QML, and it's perfect for me because I've narrowed down the startup for QML and medical. And this is based on other things that have happened in my life. And I said, I want to only do machine learning and I want to do medical. So, but yeah, I mean, it's a lot broader than I thought. Like I said, this other discussion, like I said, if anybody wants to talk about, NumPy, because PennyLane, the default in PennyLane is NumPy. But I wasn't aware that you could use NumPy solely to create, circuits and all these types of things, quantum circuits.
Well, yeah, if you do it as a state machine,
Yeah.
because in like Qiskit and a lot of other ones, they have a state machine backend that you can also use, which may be easier to manipulate. But NumPy is just a Python library. It's a module.
Yeah.
So again, got to learn Python.
And then Paul, did you have anything?
Yes. So, I mean, I think I started on this stuff kind of a while ago. And one of the big things for me was, so I was trying to do quantum machine learning like a couple years ago. I think it just struck me as like I could learn a unitary matrix the same way I'm doing all this other deep learning stuff. And then like two of the ingredients were that they supported complex exponentials and they had Einsum notation. And so I've just kind of been building quantum circuits with, Einsum for a while. I found, there's a paper, I think, Quantum Networks in a Nutshell, which just explain how to like turn any quantum diagram, which quantum circuits are one, into a summation equation. So you can just go from the picture to the math, and then with Einsum, you can take the tensor equation and then write it directly as a Python statement. I mean, so both NumPy and TensorFlow have Einsum, and of course in TensorFlow it's differentiable, and so you just write your quantum circuit out in TensorFlow, and then you can, backpropagate.
So when did this get big for NumPy with Quantum?
I don't know. I don't know that I don't even know other people using this. Kind of why I'm joining these meetups. I just want to see what other people are going.
Yeah, I mean, you'll find a lot of this. So the PennyLane, especially anything quantum machine learning in literature, there's a lot of PennyLane. And I think it's a default. Now, Qiskit has some. So I've done a couple demos. So they have like quantum convolutional neural nets. They have, I think, two other ones. Base estimator. They have, neural net work. So, I think the bulk of it is PennyLane for QML, and then you'll start to see other things, like I said, I'm interested. So if you have physics in a quantum simulator, can you modify the physics in order to get better, data results, like better accuracy, those types of things? And somebody told me that that's Qiskit dynamics. So there's many, if that's a platform, there's many things under it. But yeah, like I said, for QML, I typically in literature run across PennyLane.
It makes sense. You said you said there's something dynamic, so that they do have like ideal gas simulators or whatever.
That's what it sounds like. I haven't gotten into it yet. It was just I was on that forum, and a lady had recommended me to go use it, and that seems like that's in that right place, right? So I think it's more like, what if you did this and the quantum computer had this at some point, then you could use your quantum simulator right now as if the physics, or not the physics, but like the way the quantum computer would act in 2 years from now, then you'd be ahead, basically.
Yeah.
So yeah, you'll find many things under that, and they just finished up, summer school, the whole thing. So I had shared a couple links in here. So I don't know, Paul and other people too, have you come across those Lanol papers? So challenges and opportunities in quantum machine learning I would definitely read that one. The other one, it's I separated by commas on this one. It's basically trainability issues in quantum machine learning by these Lanol researchers, and I think there's other institutes on it, but they're like bigger, too, just like Lanol. But those are two papers I would read if you want to understand the basically the issues of QML today.
Yeah, I'm my interest in QML is starting to drift towards using QML as a layer, but ultimately trying to leverage the power of the QML in its known areas like optimization and graph. There's all kinds of graph problems that I've seen it actually demonstrate, or I've written some code in different courses that actually get some real work done. So most of what I've seen in QML, like these demonstrations, is they in some cases they use QML as a layer of the ML stack, and they just treat it as like a 2D convolutional layer, and then the parameters, like you're talking, Kevin, like it's just a big nest of RY gates. Those parameters are trained. But I think there's probably a jump there where, depending on what you're trying to solve with your ML stack, that you could custom build a layer that will optimize a specific task and not just wait for the training to train it to do something. So that's kind of where I've been looking. I've also looked a little bit into QML in some more simplistic ML operations like support vector machines and principal component analyzers and that sort of thing. And there seems to be some power there. Like if you, like in one step, support vector machines, one of the advancements was to provide the support vector machine with a kernel. And what I've seen people do is they use a quantum layer to build the kernel, and then they pass the kernel into the machine learning layer. It's pretty fascinating. But the quantum kernel builder can then like use leverage optimization techniques, again, it's more based on what the problem is rather than just letting a machine learning stack learn, and because when a machine learning stack is really doing is it's training each layer of the stack to do a specific task. You just aren't told about it. It's just all, happening like in a black box. So
Yeah.
I think that's where the real power will come from.
Yeah, and I would keep in mind with all of this is that a lot of the innovation in quantum circuits is aimed towards a quantum computer, that has a lot less noise. So for instance, parameterized quantum circuits, those were introduced in 2012, and they can run on simulators, they can run on real hardware. And same thing with on the optimization side with parameter shift rule, or differentiation, that can run on both, where adjoint, which is better, only runs on simulators today. So I think that's a main thing that's going on is there's a huge, drive, for faster, and these things aren't bad, but it's like the sole focus, faster, more qubits, these types of things, but the noise is still very apparent, with real hardware. But the whole field, and this is like Maria Shold and Seth Lloyd and other researchers too, and I would even say the Lanel researchers and Patrick Holes, the physics behind it. Like, how can we understand the data going through with rotational gates to get better accuracy, or how can this be done with quantum, qubits or qubits to get even a brand new utility? So I don't think that's nearly as explored as much as quantum speedup. So, it's just one of those things. Even if you have an exponential speedup algorithm, when you put it into like a nice hybrid model, you're still encoding data. It's called the input-output problem. So the I/O of it will likely take away a lot of the speedup with the exponential speedup algorithm. So I'd say a lot of people are after that algorithm, but I think a lot of them already exist. This is not a new field. I mean, Paul said, there's a paper that goes back to the 90s with a lot of this, without, quantum algorithms.
Yeah, I think everybody's accepted that the quantum in ML right now won't make the process faster. They're hoping it'll make the predictions better or more precise. But a lot of that, I guess, remains to be seen.
And then, Paul, did you have something?
Just on the discussion. So I have similar views. I mean, it seems honestly, I started looking at quantum computation like in my undergraduate. I thought, oh, I'm going to go do quantum computation, and so I just studied the heck out of physics and math and everything I could, and then I was like, wait a minute, this is useless. Like, what am I going to do with this stuff? And then so just kind of wandered around until I eventually became like a machine learning engineer. But then I guess what struck me a couple of years ago was that I realized I had dropped all my QC learning, but I understand it better now because I've been working with deep learning for so long. And the thing that kind of I feel like deep learning models are really trying to learn physics, right? Like we're showing them images, we're showing them human generated text, whatever. But at the end of the day, those are just outputs from some physical system, and that physical system is driven by some unitary operation. So at the end of the day, we're maybe really trying to learn some unitary operator. Like that's what it is. There's some unitary operator that simulates our eyes and our brain. And I think this may be, I know there's there's a lot of questions to whether or not the human brain uses, that there's no evidence, and there's a lot to suggest that our brains are entirely classical information computers. But I'm not entirely sure. But what I do know is that underneath all of it is a unitary system, what I believe to be a unitary system. And so I'm like, why wouldn't maybe there is some benefit to trying to learn that directly. And so I don't even think there's no algorithm that, it's challenging because I found it's harder to learn things with a unitary model. So I'm still missing something. But they should be just as capable. It is a universal computational system that should be, a unitary matrix should be just as possible. Some arrangement of unitary matrices should be just as powerful as any deep learning technique. And they would hopefully make use of some property, the way information is organized in the universe, to do things that deep learning systems are, struggle with. And so that's kind of the circuit I'm looking for, right? Like, what is it that's easier to learn? Is there some system, is there some problem that is easier to learn as a unitary matrix than as a transformer, which is and honestly, I'm struck by the similarity between transformers and like field theories, right? It's just a big dot product between, I don't know. It's really loose, but it just seems like we really should, deep learning systems really should be converging to simulating some universal physical system. So kind of keeps me up at night.
Yeah, I mean, that's interesting. It makes sense. Find the unitary. And I don't know about replacing a transformer, and some of the other conversations we've had, like maybe the new, this layer is quantum and it trains on its own. It does its thing well. And I think a lot of it is just, if we have so many different, data files or images that you're throwing at a quantum circuit, I don't think it's known exactly, like the exact gates and the parameter, configuration. Like parameterized quantum circuits are kind of like, they were introductory, and we should be getting into more complex systems, especially better simulators, better hardware, those types of things. But I don't know. I think a big paper's on the horizon, because I've seen a lot, because they've tried training the embedding, and they've tried, all of this work with, a lot of times CNOT gates don't help a lot, for specific tasks, and are GPU consuming, time consuming, those types of things. All right, Ron, any last questions here or comments?
This is kind of off the subject, but just wanted to let you know, Kevin, I ran across a supplier that is claiming to sell diamond nitrogen vacancy crystals for like $200 a piece. It's just a crystal mounted on something.
Well, I guess, is this nanoscopic, or like, what's the size of it?
It's 3 millimeters by 3 millimeters by like half a millimeter.
Well, that's pretty big then. Yeah.
Well, it's obviously not one center. It's 1 part per million, or 1 part per billion. So it's got a whole bunch of nitrogen vacancy centers. Plus, this is their crummiest product. It's got because it's got a high nitrogen count, and it's also got boron contamination. I don't know where the boron comes from, but they're all it's a crystal created using chemical vapor deposition. So it's in a high pressure, or very, very high energy system, where they're dropping these basically carbon ions onto a surface, and then injecting the nitrogen somehow. But I just thought you might find that interesting. It's $200 for a 3 by 3 millimeter by 3 millimeter by less than half a millimeter thick crystal, and you can supposedly shine light on it and get it to do things. Well, we will be seeing.
Yeah, I mean, I appreciate you bring that up. This discussion has seen many discussions with quantum sensors and nitrogen vacancy centers and all that. So if you want to download the chat, it's the triple dot, and then you can download that. There's some good links in there that you could see. And then this has been discussion 97 for how to succeed in PennyLane library for medical QML developers. My name is Kevin Krawczyk. I'm founder CEO of Chemical Q Device. Have a good rest of the night, and have a productive rest of the week, everybody. Take care.